And actually the answers or the questions that I'm doing here, they're the more important ones. So these are the ones that you really, really need to know to be on track. Okay, so then the topic today is actually a brief introduction to random fields. Because as you might have realized by now, the whole thing is called random field theory-based p-values, which are these p-values that you see in the SPM table. And of course, this rests on then the notions of random fields. And random fields are, if you take probability courses, they're not the first thing that you encounter. Actually, the very first thing that you encounter are elementary probabilities of sets, and then at one point you encounter random variables. The problem with random fields is that they are generalizations of random processes or stochastic processes, which in turn are generalizations of random variables. So it's actually, this is why you need to know what a random variable is, so that you can deal with the definition of random fields. The reason why we talk about random fields again is, if you remember from last time, that we are interested in creating a null distribution that extends over space. So last time I showed you this kind of T-map thingy that looked like this, and then I said we want to create a null distribution from which you can sample things like this or like this or like this. Yeah. And these black lines these black lines here that are just drawn, they are supposed to be realizations of random fields in one dimension. If you want a fancier first look at random fields, then maybe look into the handout. Oops. There we will get to these figures, but what this shows here in this, you can also draw on here. What this shows are 2D random field realizations. So you see that it looks not completely random. There are some blobs if you want, but these blobs are somehow randomly allocated. There's a pattern here if you go from the upper left to the lower right. So these are visualizations of realizations from random fields in 2 dimensions. And here there are some more realizations of random fields which are of different types. So they can look fairly different. And of course, what we are thinking about when we talk about fMRI, then we are thinking about a random field in 3D, but that's not really that easy to visualize. So you might think if it was, so it's definitely not, but you could think that you kind of make slice-wise pictures of a random field in 3D, and then you can make a movie going through a 3D random field. So this is kind of the visual first glance at random fields. But what I really want to go over now are definitions for random fields. And we need these definitions to then build on them to basically study the random fields that are of interest in random field theory-based p-value evaluation, and also to study specific aspects of these random fields. Keep in mind all the time that we're using these random fields to create a null distribution. Yeah? So we are not trying to explain something that some effects that extend over space. So we are not trying to find random fields that have a peak somewhere and then maybe another peak somewhere or something. We are trying to find random fields that are null distributions, so that randomly have some peaks somewhere, but that don't have systematic effects. Yeah. So null distribution. So we're trying to use random fields as a null distribution. Okay, good. Now let's get started and start with definitions. So definitions are, if you read mathematical or semi-mathematical texts, they are usually easy in the sense that you don't have to ask yourself why. I mean, you can ask yourself why, but you don't have to ask yourself why, because they don't follow from anything that you read before. They are just new and they are like that. You can ask yourself why, but then the answer is some pages down the line. So it's the power of definitions is always, like I said, I think last time already, is that they are chosen in a way that something else makes sense. So then let's just get started. With real-valued random fields. Maybe one historical note before I really get started is this, that random fields for null distributions in fMRI were introduced to the literature. That happened in 2 papers from 1991. I think that was a Friston paper, roughly, and then 1992, definitely in a Worsley paper, which was still in the domain of PET. So these insights were then later transferred to fMRI. Especially the Worsley work that goes back to work by Adler. From 1981 and earlier. Yeah, so this is basically the history. So although you might find these things pretty advanced somehow, they are actually not that novel in the sense that it just happened like last year or something. So this is, another way to view is that this is actually standard knowledge because it's old. Okay, so what is a real-valued random field? Let's start with the first definition, and I write it down. A real-valued random field, which I abbreviate, a real-valued random field. And for the moment, I write it like this: big X, small x, x in S, on a domain S, subset of the real numbers to the power of D, is a set of random variables. So this is why you need to know what a random variable is. On a probability space. This is a little bit redundant because random variables are always on probability spaces. Omega R P. And then follows a little bit of an explanation. This means that for each small x in S, this thing x, which maps from omega to R, is a random variable. So that's the definition of a real-valued random field as we will use it here. Then if you look into the script, there's like a one page of text then that tries to explain this definition, and this is what I also want to do now. So yeah, let's go step by step. So first of all, the real valued random field exists on a domain S, a subset of the real numbers to the power of D. So this will happen throughout the course. So this big D is the dimension of the domain, and the D's we have in mind are actually D1 for this one-dimensional random field, which is also called a stochastic process or random process. D2 for the pictures that I just showed you, and D3, D3, so three-dimensional space for fMRI proper. Yeah, so this can go, of course, to higher dimensions, but yeah, so things get quite easy if the R to the power of D is just one-dimensional real numbers. Then a lot of things simplify. D equals 2 is nice for making pictures, and D equals 3 is the case that we are actually interested in fMRI. And this S is a subset, so that's a certain domain. So the thing that I always have in mind when I think of this S in terms of fMRI, it's the brain. Yeah, so that's the subset that we are interested in because we image the brain, and then the subset of the three-dimensional space that we are applying this whole thing to is, of course, the brain. Okay, that's okayish. The question now is really what the definition wants to say, in the sense that we have a set of random variables. And this is what we have to think more about. So there are different ways to write random fields. And in the theory, the random field theory for p-values, especially the stuff that Worsley writes, random fields are always written like this. XX in S is a random field. So you find that in the whole fMRI literature on this, it always says XX, or sometimes then this is the random field has a different denotation. So for example, if it's talking about a T field, then it says T of X is a random field. Also, sometimes you find that then the X, the small x, is replaced by an S. So you find, of course, variation in terms of the precise letters, but it's always in this format. So you have a big thing, and then you have a small thing, and then it's that. So what is that supposed to mean? So the definition says that this XX is a random variable. This is a random variable. So what this implies is that the whole thing, so XX, is a random variable. That means it takes elements from the elementary outcome set and maps them onto the real numbers. So it takes an omega from the elementary outcome space and maps it onto XX of omega. Now, this is a little bit of a weird notation in the sense that here you have this kind of joint symbol that looks almost like something that I just told you you shouldn't do, because it looks like that the x, the big X, it looks like the value of the function x, so big X, at the location small x. And this is why this notation is, it's okay-ish, but it's, and I will use it throughout, but there are better notations actually. So I think a clearer notation for the whole thing is that you write a random field like this. So it takes values from the domain crossed with the elementary outcome set and maps them onto the real numbers. And thus takes a small x, an omega, and maps that onto x omega. Yeah. So what is this supposed to mean? Well, the first thing is that the small x is an element of, let's say, R3. Yeah. So that indexes a location in space. If you want, if you are in 3D, then it's definitely in the 3D space. Location in space. Of course, you can also have 1D space or 2D space. That's a location in space. And the omega is, of course, the small omega, an elementary outcome. So from the idea of a probability space modeling a random experiment, we already discussed last time that the idea is that you have this omega, so this big omega set on which you have a probability measure, and you can now draw at random, according to the probability measure allocated to the subsets of omega, or even to the elementary outcomes, you can draw an omega. And then we discussed how this leads to random values of random variables. So you draw this at random. So this essentially means that these omegas here are random. Yeah, and drawn according to the underlying probability measure. Now, what the whole thing then means, especially if you look at this like that, like I've written it down here, is that you select an omega at random. So let's say we select this omega star, and then we have random variables at each location in space that give us real numbers. Yeah. So let's draw it like, or write it like this. So what this is supposed to mean is that we select an omega star at random, and when we put it into the random field, this random field gives us real values for all points in space, and the values that it gives us are real numbers. Yeah, so you have to maybe get a little bit used to that space. So this small x can be 1, 2, or 3-dimensional, but the value that you get from the random field, at least in what we are doing, is always 1-dimensional. Yeah. So this refers to the fact that I showed you we have 1-dimensional space, and then you sample from it and get something like this. So of course this black curly line here, that's just a real number. The same thing when I showed you these plots earlier. You have 2-dimensional space, but what you plot is something 1-dimensional. Yeah. So the values that these random fields take on, they are 1-dimensional. Now the crucial thing is that the fact that the random field is defined for all x in S makes these essentially functions, but functions that are not further specified. So think again if you of what one could call a multivariate, let's say 3-dimensional function. So something like this. And as I told you, you should read up on the calculus. So in the calculus section, these things are called multivariate real-valued functions. This then gives you a value of x, y, and z. Maybe think about the potential field, so the scalar field in EEG, that was also a function of 3 input arguments that returned a single value. And let's say, for example, the value here is x plus y plus z. So it needs to be a single value, and here I just sum them. So these are functions that you know. So these are multivariate real-valued functions. The random field also corresponds, especially if the d equals 3, to a function like this, with 2 differences. First of all, it's not told to you how to compute the value of the function based on the coordinate. That's just not specified. And these functions, these things here, they are chosen at random. Yeah, because they are indexed by these omegas. So another way to write this is that a random field, you can also write it like this. You have you can view it as a function over space. So let's say it's defined on S, which is a subset, let's say, of the 3-dimensional space, and this gets mapped onto the real numbers. And takes on it takes in values in the set S, which get mapped onto x. Yeah. So there are essentially 3 or maybe even more ways to write random fields. The most important thing that you need to get your head around and get into your heart is that random fields specify functions over space. We are talking about real-valued random fields, so we are talking about real-valued functions. So the values that these functions are taking on are real numbers. These functions over space are not specified in terms of things that you typically associate with functions, so that you, for the input argument, you get a formula how to compute the output argument. This is left open. And most importantly, these functions are random in the sense that there is an underlying probability space from which omegas are chosen. Then this omega is fixed for a given function, and then you have one realization of the function. Yeah. So an example, if you're familiar with random processes, is of course things like Brownian motion or Ornstein-Uhlenbeck processes, or all these things, or even random walks, or drift diffusion models. Who has heard about the drift diffusion model? Yeah, so that's a random process, which is a special random field. And in the drift diffusion model, you can also view this whole thing as a function. In the drift diffusion model, you have, of course, here you have time, and then you have something drifting, and this thing here is essentially a function. Let's call it f, and it's parameterized by an omega that was drawn from an underlying probability space. Yeah. So if it helps, I don't know what helps, but if it helps, you can view random fields as generalizations of your drift diffusion model, but with a domain that is not time or not one-dimensional space, but more than a one-dimensional space. For example, 2-dimensional or 3-dimensional space. Yeah, if that helps, I don't know. The more standard view is to view random fields as I have defined them. One thing that I haven't mentioned yet is this kind of sets of random variables, and this is actually quite important. So another way to view that is the following. If we're now taking again one-dimensional space, then so this is R. Then we have a lot of random variables. So for each x, and there are infinitely many, but we can of course select a couple. so x1, x2, x3, we have random variables here. Yeah? So we have a random variable x1, we have a random variable x2, we have a random variable x3. So this is what this says is a set of random variables. We have, and this is the crucial thing, we have infinitely many of these random variables because there are infinitely many values in the real numbers, in any subset of the real numbers. So we have really, really many random variables, and each of these random variables, of course, can take on values. They're real-valued random variables, so we can sample, for example, this one, we can sample this one, we can sample this one, and then we can connect these, maybe like this, and then again we have a function. So this is now a visualization for one-dimensional space. So yeah, that's then maybe the last thing to say about this. Random fields are collections of infinitely many random variables. Yeah? And last week you learned what a random variable is, and this week you learned that there can be really many random variables which are indexed by all points in space, and these are called real-valued random fields. So that's a fairly general definition. We will make this more concrete, and I will also tell you how to generate samples from random fields so that you get more of a computational impression. Questions about this general part right now? No, okay. So maybe a couple of remarks that don't really explain the definition further, but maybe explain a little bit why I write it like this. So first of all, I take this, the big letter X, for a random field because we will also look at T random fields, F random fields, and Z random fields. And I wanted to reserve these letters and also Gaussian random fields where I use the G. I wanted to reserve these letters, so this is why I take the big X. Why do I take the small x? So that I have this strange XX thing. Well, at least from my perspective, if you have a space, you rather call that X. If you have something called, if you look at random fields over time, which you can of course also do, you can also look at spatial-temporal random fields, then you would use a T. So I think X is still kind of or the small x is the most intuitive for space. What I will do in the following is always when we talk about three-dimensional space, I will write the coordinates of three-dimensional space as x1, x2, and x3. So you can think of, I think in general you think about the coordinates of 3D space as x, y, and z, which is also how it's coded in SPM. But then I'm already wasting two more letters, which I don't want to do, so because there's a lot to talk about. So I'm using x1 and x2 and x3 to denote the coordinates of space. Why do I call the set where these x's in are S? Why do I call that S? Because in the fMRI literature, this refers to the brain, but is called, so I could have taken also B, but is called search space. For reasons that will become clear later. So this is why I call this S, and something else. Yeah, I mean, we're looking at real-valued random fields, so the values that the random variables take on, they are always in R. You can have vector-valued random fields, so you can also have something like this, but we stay away from that. And yeah, then keep in mind that if X is in R, this whole thing is called a random process or stochastic process, like the drift diffusion model, or in machine learning, Gaussian processes. So you might know the work by Karl Rasmussen in machine learning on Gaussian random processes. These are special cases of random fields. Yeah? So random fields is a pretty general concept. Good. Yeah. So questions about the general definition. It will get clearer over time. but you should memorize it. Memorize it so that you can say it, and then once you are able to say it, you will also start thinking about it, and then be able to know what it really, really means. Good. One thing that I told you about these functions that are implicit in random fields is that they are not defined like in these little formulas that you know from undergraduate or high school mathematics. So something like fx is given as x squared. This you don't find for random fields, but nevertheless, one somehow has to define random fields a little bit more. To do that, we will now introduce the expectation variance, autocovariance, and autocorrelation functions. So that's the next topic. Maybe one remark before that. It is which I didn't put into the handout. One can define random fields in general by their finite marginal distributions. So by selecting points in the search space and defining finitely many. So by selecting these xi in the domain of the random fields where I goes from 1 to a finite number n. And it's actually a big result in random field theory / random process theory that by defining these finite distributions, you define the whole random field, and the other way around, if you have the random field, then these are always defined. So that is known as the Kolmogorov theory. But we are not really going down that route, so this is why you don't find this in the script if you start reading other introductions into random fields. So that was the final remark. Now, because this is with the finite distributions also a way to be a little bit more specific in terms of the definition of the random field. And another way is to use these expectation, variance, autocovariance, and autocorrelation function. Functions, and this functions refers to all of them. Yeah? So there's an expectation function, there's a variance function, there's an autocovariance function, and there's an autocorrelation function. And this should make some immediate sense to you if you looked a little bit into the script on expectations of random variables. Of course, for a single random variable, you have an expectation and you have a variance. For two random variables, you also have a covariance. Now, I told you we have infinitely many random variables that we can view as being distributed over space. So, of course, we can now, for each of these, of the infinitely many random variables, compute an expectation. But if we do so, then, of course, the expectation value is also indexed by space, which means that it becomes a function, which is the expectation function, essentially. And, we will go over them. And I think because I haven't discussed the expectation and the covariance and the variance last time, I will, once I tell you what these are, then go back and also tell you or remind you of what expectations actually are. So this is now the topic, and this is our second definition. For a real valued random field, which I now always, with the conventions of the fMRI literature, specifically the Keith Worsley literature, write like this. So I could also write nothing or just one letter or something, but I will always say a random field x of x, where x is in the domain. So this is how I will write it now. For a real valued random field xx, x in S, the expectation function that is what is being defined here, is defined as n, which takes in values in S, which is a subset of space, one-dimensional, two-dimensional, three-dimensional space, to the real numbers. And it takes in, of course, a coordinate of space and returns the value of that. And how is that defined? Well, it's defined as the expectation of the random variable that, if you want to call it like that, sits at location x in S. Yeah, so that's the random variable that sits at xs. So if you think about one-dimensional space again, you have, of course, infinitely many values x in this. Let's call this interval here S. So that's the interval S. And you have infinitely many random variables in there. We can select some if you want. So let's select these here. And then what this definition says is that you should now compute the expected value for the random variable that sits at x1. Also for the random variable that sits at x2, and so on for all infinitely many random variables that are in this subset of the real numbers. No, it's not, definitely not like that. Subset of the real numbers. And this is how you get the expectation function. So, does any one of you remember what the expectation of a random variable is? Anyone feeling capable of defining the expectation of a random variable, or given an intuition of the expectation of a random variable? Either is fine. Nobody of the master students? No? Okay, so intuitively the expectation of a random variable is the value that the random variable takes on over many repeats of the random experiment. So it's always a number in the range of the random variable. So expectation or expected value, expectation slash expected value these are analytical properties of random variable. I think everybody of you can tell me what the expected value, let's say if we have a random variable x, which is distributed according to a univariate Gaussian distribution with expectation parameter mu and variance parameter sigma square. Everybody, I think, can tell me what the expected value of that is. So what's the expected value of that? Exactly. So, which is here a special case because the parameters of the distribution and the expectation and the expected value actually are the same thing. In general, so in really, really general terms, the expected value of a random variable is defined as an integral. And I think this is the only time that this integral will actually show up. I hope. So far I'm trying to make the whole course without Lebesgue integrals. So, you know, there's Riemann integration in your calculus section, so you should know about Riemann integrals because these are the integrals that you're familiar from school with. But Lebesgue integrals you're not familiar from school with, and I'm trying to avoid them. Nevertheless, here it actually doesn't hurt to show them. So this is how one defines the expected value of a random variable in all generality. But it's also informative. This is why I'm doing it here. So you get the value of a random variable if you think about this as follows. So you take all the values that the random variable can take on. So this is what this means. And also what this integral over the entire elementary outcome space means. And this is what you allow yourself to do, put in a multiplication dot in here. You multiply them with the probability measure that you assign to each of these elementary outcomes. Yeah? So this is a very general way to write something that you are actually more familiar with, namely the expected value of a more or less familiar with the expected value of a discrete a random value that takes on values in a discrete outcome set, which is given by a sum. So you just sum up things, and what you sum there is the values of the random variable for each of the omega I. Actually, this is these are two things. This is a random variable that takes on a discrete number of values on a discrete probability space. And you multiply them with the probability of the elementary outcomes. So classic examples of course, always the die with 6 sides. So what's the expected value of a die? Exactly. Because you have to do 1.6 times 1 plus 1 over 6 times 2. Doing it a little bit further, faster, and hopefully not forgetting something. And this is 3.5. You see that this expected value is also, you see that it's a single number, which also reminds you that integrals are just single numbers. It's a single number, and it's also not that meaningful in the case of the die, because although it's what you get if you throw the die, write down what you get, make a long list, and then average this list in the end over all the observations. It's not something that you will actually observe on a single outcome, right? So because you will either see 3 or 4 on a single outcome, or 2 or whatever of the 6, but you will never observe actually a 3.5. So the expected value is a theoretical summary measure of a random variable. It's a single number, and actually for the Gaussian. The Gaussian, of course, is defined in terms of a probability density function. And then in terms of a probability density function, one can actually, if one has a probability density function, so if one has a random variable with a probability density function, then one can compute the expected value using Riemann integrals. So basically the way you are familiar with doing integration, by computing the antiderivative and then using the central theorem of analysis, or the central, or what's it called, the central theorem of calculus, where you put in the upper border and the lower border. This is actually an indefinite integral, so you have to be a little bit more relaxed in this case. But this you can then actually compute. The problem is always with these Lebesgue integrals, they are the most general definition, but you usually don't know how to compute them, or I don't know. For discrete outcome spaces, you know how to compute them. It can be a little tedious because you have to write it all up. With random variables that have probability density functions, because their distributions have probability density function, you then can solve an integral. And the easiest is then always to go to Wikipedia, because these kind of integrals have, of course, been computed. So if you find your new favorite probability distribution that has a density, let's say the beta distribution or the Dirichlet distribution, or I don't know, whatever, gamma distribution, and you wonder, what's the expected value? Just go to Wikipedia. Somebody will have computed this for you, and you will find the expected value. For the Gaussian, we discussed already that you actually then get out mu. Here I called the probability density function f because there are a lot of p's everywhere. Of course, in like machine learning style, you will find something like this for that, where p of x then means the probability density function. Good, so these are expectations, and expectations are linear. This is something that I think we will need when we talk about the variances. So expectations are linear. So if you have a random variable x and it's multiplied by a scalar, a real valued scalar a, and you add to it the multiple of a second random variable y, then this actually corresponds to the expected value of x plus times the scalar times the expected value of y. And this linearity just follows from the linearity of integrals. And the linearity of integrals in the Lebesgue case, you can, even if you don't know what Lebesgue integrals are, you know that what Riemann integrals are, and you also hopefully know that Riemann integrals are linear, and Lebesgue integrals are also linear. Good. So essentially, the definition of the expectation function then is that you have to compute these, either compute or define, and we will actually often define them, these expectations. And before the break, I'm just telling you an important thing for random field based p-value stuff, namely that the fields we are interested in, they are, and we will come back to that, but they are defined in a way that the expectation of each of these random variables is 0, which you should link to your notion that we use random fields here as null distributions. Yeah? So we use random fields that have an expected value of 0 everywhere over space, because we want a null distribution over space. Yeah? We want to, we then have, of course, our observed effects, but we want to compare our observed effects with a null distribution. And of course, you're familiar with the t distribution, which is centered on 0, or z-tests, which are also centered on 0. And exactly the same way, the random field that we then use to model the errors in random field theory-based p-value correction, they are centered on 0. Yeah? Good. Let's have a break now and continue 9:15.